What if I told you a single Belgian engineer solved a physics problem that General Motors, with all its billions of dollars in research funding, couldn't crack? A problem so fundamental that every car you've ever ridden in still suffers from it, unless it uses his brilliant idea. This is Motorsport heritage, and I spend way too much time thinking about suspension engineering. If you're someone who geeks out over the hidden technology that makes cars drive the way they do, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Here's the thing. We take car suspension completely for granted. You get in, you drive, and unless something is broken, you never think about what's happening between the wheels and the body. But suspension is the single most important system in any vehicle. More important than the engine. More important than the brakes. And I know that sounds wild, so let me explain. Your engine makes you go. Your brakes make you stop. But your suspension is the only thing keeping all four tires in contact with the road. And if your tires aren't touching the ground, nothing else matters. You can have 1,000 horsepower and carbon ceramic brakes the size of dinner plates, but if your suspension lets a wheel lift off the pavement, you've got a very expensive paperweight sliding sideways toward a guardrail. Look, the problem that haunted automotive engineers for decades was deceptively simple. How do you make a car comfortable and sporty at the same time? It sounds easy until you realize these two goals are fundamentally opposed. They are enemies. They genuinely hate each other. Think of it like a mattress. A soft mattress feels amazing when you lie down, but try doing push-ups on it and you sink right through. A firm mattress is great for exercise but terrible for sleep. For most of automotive history, engineers had to pick one. Soft for comfort or firm for handling. There was no in-between, and everybody just accepted that as an unchangeable fact of life. By the early 1950s, this compromise had reached a breaking point. Post-war prosperity meant people weren't just buying cars to commute anymore. They wanted luxury. They wanted performance. They wanted to cruise across France at highway speeds without spilling their espresso and then carve through alpine switchbacks on the weekend. The market was demanding the impossible, and every major manufacturer knew it. Conventional steel spring suspension hadn't meaningfully evolved since the 1930s. You had coil springs or leaf springs, a set of shock absorbers, and that was your lot. According to data published by the Society of Automotive Engineers, a typical 1950s family sedan experienced body roll angles exceeding 15 degrees during aggressive cornering. 15 degrees. That's roughly the incline of a wheelchair ramp. Imagine your entire car tilting that far every time you took a highway off-ramp at speed. Your passengers would be sliding across the bench seat like luggage on a cross-channel ferry in a storm. If you stiffened the springs to reduce that lean, you solved the handling problem but created a new one. Every crack, every pothole, every expansion joint on the highway would slam directly into your spine. Mercedes-Benz, arguably the finest luxury car manufacturer of the era, struggled with this exact trade-off. Their engineers were brilliant, but even they couldn't bend the laws of physics with steel alone. General Motors took a different approach, and honestly, it was kind of lazy. Their solution was mass. Make the car so heavy that it simply plows over imperfections through sheer inertia. A 1955 Cadillac weighed over 2 tons. That's roughly the weight of a modern Ford F-150, except the Cadillac had about a third of the structural rigidity. It worked on smooth American interstates, but put one of those land yachts on a winding European road, and it handled like a waterbed on roller skates. Meanwhile, in Paris, a small French company called Citroën was thinking about the problem entirely differently. Citroën had never been conventional. Their founder, André Citroën, was the Henry Ford of France, obsessed with mass production and radical engineering. By 1954, the company was deep into development of their next flagship, internally called Project D. This car needed to be a statement. It needed to prove that French engineering could outclass Detroit, Stuttgart, and Coventry simultaneously. And that's when they handed the suspension problem to a quiet Belgian engineer named Paul Magès, a man most automotive historians still barely mention today. Now, you might be thinking, wait, a Belgian? Working for a French company? On a problem the biggest corporations in the world couldn't solve. And yeah, that's exactly what makes this story so good. Magès wasn't a famous name. He wasn't a celebrity engineer like Ferdinand Porsche or Colin Chapman. He was a hydraulics specialist who had spent his early career working on industrial equipment, pumps, valves, pressure systems. He thought about cars the way a plumber thinks about pipes, not the way a race car designer thinks about lap times. And that outsider perspective turned out to be exactly what the automotive world needed. Because while every other engineer was trying to make steel springs slightly better, tweaking rates and lengths by fractions of an inch, Magès was asking a completely different question. What if we got rid of springs entirely? That question would lead to the most radical suspension system ever put into production, a system so advanced that when it debuted in 1955, journalists literally used the word magic to describe it. And the beautiful irony is that the technology Magès invented didn't just solve the comfort versus handling problem for one car. It laid the groundwork for every modern air suspension system you see on luxury vehicles today. But I'm getting ahead of myself. To really appreciate what Magès pulled off, we need to understand exactly how his system worked, and trust me, it's more elegant than you'd expect from something operating at pressures higher than a scuba tank. And it all started with a simple metal sphere. So here's what most people don't realize about suspension design. Steel springs are incredibly dumb. I don't mean that as an insult. I mean they literally have no intelligence. A steel spring responds to force in a perfectly linear way. Push it with 10 pounds of force, it compresses 1 inch. Push it with 20 pounds, it compresses 2 inches. The relationship never changes, never adapts, never thinks. It's the same whether you're cruising on glass-smooth asphalt or bouncing over cobblestones at 60 miles per hour. Magès understood that the real world isn't linear. Roads aren't linear. Driving conditions change constantly. So he needed a spring that could think, that could adapt its behavior based on what was happening in real time. And his solution was breathtakingly elegant. Instead of steel, he used gas. Specifically, nitrogen gas sealed inside a metal sphere about the size of a grapefruit. Picture this sphere divided internally by a flexible rubber diaphragm. On one side of the diaphragm, you have high-pressure nitrogen. On the other side, hydraulic fluid connected to the suspension cylinder at each wheel. When the wheel hits a bump, hydraulic fluid rushes into the sphere and compresses the nitrogen gas. The gas pushes back, absorbing the impact. Now, here's where it gets really interesting. Gas doesn't behave like steel. Gas follows Boyle's law, which states that pressure times volume equals a constant. As the volume decreases, the pressure increases exponentially, not linearly. This means the suspension is soft and compliant over small bumps. Your morning commute feels like floating on a cloud, but it progressively stiffens as impacts get bigger, preventing the car from bottoming out over large potholes or speed bump. No steel spring in existence could replicate this progressive characteristic. It's like having a mattress that's simultaneously soft and firm depending on how hard you push on it. But the gas sphere was only half the genius. The other half was the height control system, and this is where Magès really separated himself from every other engineer on the planet. He designed a mechanical height sensor for each wheel. Think of it as a tiny lever connected to a valve. When the car's body dropped below its predetermined ride height, say, because you loaded the trunk with luggage, the lever would detect the change and open a valve, allowing high-pressure hydraulic fluid to flow into that wheel's cylinder, raising the car back to its correct position. If the car sat too high, the valve released fluid back to the reservoir. The entire correction happened in under 2 seconds. The operating pressures were staggering. We're talking about 2,500 psi, or roughly 175 bar. To put that in perspective, your car tires operate at about 32 psi. A commercial scuba tank sits around 3,000 psi. So Magès was running hydraulic lines at pressures approaching deep-sea diving equipment inside a family sedan on public road. That's insane when you think about it. These extreme pressures meant every component had to be manufactured to aerospace tolerances. A single leak wouldn't just be annoying, it would be catastrophic. Citroën had to develop entirely new manufacturing processes, new seal compounds, new metallurgy for the hydraulic lines. The pump alone required precision that exceeded anything in automotive production at the time. According to internal Citroën engineering documents later archived at the Conservatoire Citroën in Paris, the development team redesigned the hydraulic pump 7 separate times before achieving acceptable reliability. And look, the early prototypes were disasters. I want to be honest about that because it makes the eventual success more impressive. Seals burst under pressure. Lines ruptured at connection points. The system would work perfectly for a few hours during testing, then fail spectacularly, dropping the car onto its bump stops with a bone-jarring thud. Citroën executives were getting nervous. Project D was consuming massive resources, and some board members pushed hard to abandon Magès' system entirely and return to conventional steel springs. But André Lefebvre, Project D's chief engineer and a former aircraft designer, believed in the vision. He gave Magès more time, more resources, and more freedom. Magès and his small team worked 18-hour days, systematically solving each failure point one at a time. They developed new synthetic seal materials that could withstand both the extreme pressures and the wide temperature variations between a French summer and a Scandinavian winter. They tested different diaphragm compounds for the spheres. They refined the valve timing down to millisecond precision. By early 1955, they had a working system. But working wasn't enough. It had to be bulletproof. Citroën's entire reputation would ride on this technology, and they knew the automotive press would be watching closely for any sign of failure. So they subjected prototypes to torture tests that far exceeded anything a customer would ever experience. Cars ran continuously for weeks at maximum load over Belgian cobblestones, some of the roughest roads in Europe. They tested in the Sahara Desert's brutal heat, where ambient temperatures exceeded 50 degrees Celsius, and in Scandinavia's Arctic cold, where hydraulic fluid could turn to sludge. The results were extraordinary. The hydropneumatic suspension delivered ride quality that matched or exceeded Rolls-Royce, which was universally considered the gold standard of automotive luxury. But unlike a Rolls-Royce, which wallowed through corners like a yacht in heavy seas, the Citroën stayed flat. Body roll was reduced by approximately 70% compared to conventional suspension. Brake dive and acceleration squat were virtually eliminated. This is where it gets really interesting, though. The system offered capabilities that no conventional suspension could even dream of matching. Need to change a tire? Push a lever and the car would rise 6 inches, making a jack completely unnecessary. Driving through a flooded road? Raise the suspension to maximum height for extra ground clearance. Want sportier handling? Lower the car for a reduced center of gravity. One car, multiple personalities, all controlled by hydraulic. The system could even compensate for uneven loads automatically. Load heavy cargo on one side of the trunk, and the system would level the car within seconds. Lose a wheel entirely, and the remaining 3 hydraulic cylinders could support the car's weight, allowing the driver to limp to safety at reduced speed. This wasn't just a suspension system. It was an active chassis management platform decades before electronics made such systems common. When the Citroën DS finally debuted at the 1955 Paris Auto Show, it caused an absolute sensation. The car looked like it had arrived from another planet. Sleek, aerodynamic, futuristic, with a drag coefficient of 0.36 when most contemporary cars were above 0.50. But it was the suspension demonstration that truly stunned observers and left journalists scrambling for superlatives. Citroen's demonstrators would load the car with 4 passengers and heavy luggage, then remove them one by one. The car maintained perfect ride height throughout, never squatting, never rising, never bouncing. They'd disconnect the rear hydraulic spheres while the car was driving, and it would continue normally on just the front suspension. They drove the car on 3 wheels. Most dramatically, they'd have someone stand on the rear bumper, then step off, and the car would immediately self-level without any bounce or oscillation whatsoever. Orders flooded in at a rate nobody anticipated. On the first day alone, Citroën received 12,000 orders. By the end of the week, that number had climbed to 80,000. To put that in context, according to production data from the French Automotive Industry Association, most European manufacturers at the time sold fewer than 10,000 units of any single model per month. Citroën had a year's worth of production backlogged before the show even ended. The motoring press was unanimous in its praise. British magazine Autocar called it the most significant automotive advance since the electric self-starter. Road and Track declared it the car of the future available today. One journalist reportedly said that watching the DS self-level was like witnessing a magic trick performed by an engineer instead of a magician. But here's the thing, not everyone was convinced, and this is where the contrast framing gets really important. Detroit's reaction ranged from skepticism to outright dismissal. General Motors engineers publicly questioned the system's long-term reliability and manufacturing costs. Ford executives called it unnecessarily complex for the average consumer. Chrysler's chief engineer was quoted in Automotive News saying, and I'm paraphrasing here, that Americans want simple, reliable transportation, not science experiments on wheels. Now, you might be thinking, well, maybe the Americans had a point. Maybe the system really was too complex. And that's a fair objection, so let's address it directly. The real reason for American resistance was far more complicated than engineering concerns. Implementing hydropneumatic suspension would require massive factory retooling. It would obsolete billions of dollars in existing spring and shock absorber manufacturing infrastructure. It would require retraining entire workforces across thousands of dealerships. And most importantly, it would require admitting that a small French company with a fraction of their budget had out-engineered the mighty American auto industry. That's a bitter pill to swallow when you're the biggest car manufacturer on Earth. There were legitimate technical concerns, of course. The system added roughly 15% to manufacturing costs. It required specialized maintenance procedures that most mechanics had never encountered. The hydraulic fluid was hygroscopic, meaning it absorbed moisture from the atmosphere over time, requiring periodic fluid changes. Early production systems could occasionally be temperamental, dropping a corner if a sphere's diaphragm developed a leak. But here's what most people don't realize. These were solvable problems, not fundamental design flaws. Every new technology has teething issues. The first automobiles broke down every 50 miles. The first airplanes could barely stay airborne for a minute. Complexity alone isn't a reason to abandon innovation, it's a reason to refine it. And Magès kept refining. In 1957, he developed an improved height corrector that responded even faster to load changes. In 1959, he created a load-sensing brake valve that automatically adjusted brake pressure distribution based on vehicle load, preventing rear-wheel lockup when the car was lightly loaded. Think about that for a second. This was essentially a mechanical anti-lock braking system, 2 full decades before electronic ABS became common in production cars. Magès was solving problems that the rest of the industry hadn't even identified yet. The second-generation system, introduced in 1965, was even more sophisticated. It featured dual-circuit hydraulics for redundancy, meaning if one circuit failed, the other could maintain basic suspension and braking function. The spheres were redesigned with improved diaphragm compounds that lasted significantly longer. Operating pressure was optimized for better efficiency and reduced component stress. By 1967, Citroën introduced Duravi power steering, fully integrated into the hydropneumatic system. This wasn't ordinary power steering. The hydraulic pressure provided speed-sensitive assistance, more help at low speeds for easy parking, progressively less at high speeds for better road feel and stability. The steering was self-centering, using hydraulic pressure to return the wheels to straight ahead automatically. According to testing data published by the German automotive magazine Automotive, it was the first speed-sensitive power steering system in production anywhere in the world. The technical specifications were remarkable even by modern standard. The system could cycle through its full suspension travel 5 times per second. Response time to road inputs was under 5 milliseconds. The hydraulic pump, driven by the engine, could generate 2,500 psi continuously while consuming just 3 horsepower. The entire system weighed only 65 pounds more than a conventional steel spring setup, which is remarkable considering it included power steering, self-leveling, and variable ride height capabilities all in one integrated package. The validation that really mattered came from the most prestigious name in luxury motoring. In 1965, after extensive internal testing that reportedly lasted over 2 years, Rolls-Royce licensed Magès' technology for the Silver Shadow. Let that sink in for a moment. Rolls-Royce, the company that had spent decades perfecting conventional suspension to deliver what they called a magic carpet ride. They looked at Magès' system, ran their own tests, and concluded that a Belgian engineer working for a French mass-market manufacturer had built something better than anything their own team could produce. The Silver Shadow's ride quality became legendary. Automotive journalists described it as floating on a cloud, and for the first time, the car could corner without the dramatic body lean that had characterized earlier Rolls-Royce models. Mercedes-Benz followed suit with their experimental C111 prototype and later the 450 SEL 6.9, which used a hydropneumatic rear suspension derived directly from Magès' patents. Maserati adopted it for the Quattroporte too. Even conservative BMW experimented with hydropneumatic suspension during the late 1960s, though they ultimately decided against production implementation. But the most impressive application of Magès' technology came with the 1970 Citroën SM. This was his suspension paired with a Maserati V6 engine, and the combination was intoxicating. Supercar performance with limousine comfort in a single package. The SM could cruise at 140 miles per hour on the Autobahn while providing ride quality that let passengers read a newspaper without losing their place. It could corner at lateral acceleration levels that would have conventional cars scraping their door handles on the asphalt, yet it never transmitted harsh impacts to the occupants. The SM featured another Magès innovation that was decades ahead of its time: variable ride height based on vehicle speed. Above 65 miles per hour, the suspension would automatically lower the car by 15 millimeters, reducing aerodynamic drag and improving high-speed stability. Below 30 miles per hour, it would return to normal height for better ground clearance in urban environments. This was active aerodynamics before the term even existed in the automotive lexicon. Here's what most people don't realize about the SM's braking performance. Under maximum braking from 60 miles per hour, a conventional car's nose would dive 4 to 6 inches, transferring weight forward and destabilizing the rear axle. The Citroën's nose dropped less than 1 inch. This meant weight transfer to the front wheels was dramatically minimized, keeping more weight on the rear wheels for better braking stability. According to contemporary test data from the French automotive magazine L'Automobile, stopping distances were reduced by up to 15% compared to conventional cars of similar weight and tire specification. Cornering was equally impressive. A conventional luxury sedan of the era might achieve 0.75 g lateral acceleration before losing grip and beginning to understeer. The hydropneumatic Citroëns could exceed 0.85 g while maintaining passenger comfort. The suspension would actually firm up during cornering as hydraulic pressure increased on the outside wheels, providing progressive resistance to body roll. It was like having adaptive dampers decades before electronic control made them possible. Yet despite its clear technical superiority, hydropneumatic suspension remained a niche technology. Why? Cost was certainly a factor. The system required expensive materials and precise manufacturing tolerances that drove up production costs. But the real barrier was psychological, and this is something the automotive industry still struggles with today. The industry was deeply conservative. Manufacturers had billions of dollars invested in conventional suspension infrastructure. Dealers were trained to service springs and shocks, not hydraulic accumulators and high-pressure pump. Customers were wary of complexity, especially in an era before computerized diagnostics made troubleshooting accessible. American manufacturers actually conducted their own tests. General Motors built several prototypes with hydropneumatic suspension in the early 1960s. The results were genuinely impressive. Ride quality improved by approximately 40%. Handling improved by roughly 25%. Brake dive was virtually eliminated. But the bean counters killed it. The system would add approximately $400 to the cost of each car, which translates to about $3,500 in today's money after adjusting for inflation, according to the U.S. Bureau of Labor Statistics Consumer Price Index. For a mass-market manufacturer selling millions of units per year, that per-unit cost was considered unacceptable, even though the performance gains were measurable and significant. Then the 1973 oil crisis changed the entire conversation overnight. Suddenly, fuel economy mattered more than ride comfort. Hydropneumatic suspensions added weight and parasitic pump losses of roughly 1 to 2 miles per gallon, which became a liability in an era of gas lines and rationing. Manufacturers pivoted toward making cars lighter and more efficient, and complex hydraulic systems didn't fit that new paradigm. But here's where the story takes a turn that most people completely miss. Magès's influence extended far beyond hydropneumatic suspension itself. His work proved that active suspension was physically possible, that a car's dynamic behavior could be controlled and adjusted in real time. This insight inspired an entire generation of engineers to think differently about chassis design, and the ripple effects are still shaping the cars you can buy today. In the 1980s, Lotus Engineering developed active suspension for Formula One using principles that Magès had pioneered 3 decades earlier. Instead of mechanical height sensors, they used electronic sensors. Instead of hydraulic pressure alone, they used computer-controlled actuators. But the fundamental concept, using hydraulic fluid to actively control suspension geometry in real time, came directly from Magès's original work. The Lotus system, which helped Ayrton Senna dominate the 1987 Monaco Grand Prix, was essentially a digital evolution of an analog idea born in a Parisian workshop in the 1950s. Modern air suspension systems are direct descendants of hydropneumatic suspension. Replace the hydraulic fluid with compressed air, swap the nitrogen spheres for air springs, and you have the basic architecture used on today's luxury vehicles. The Range Rover, the Mercedes S-Class, the Audi A8, they all use air suspension that operates on principles Magès established over 60 years ago. The height sensors, the automatic leveling, the variable spring rates, it's all there, just implemented with different technology and electronic control. Even more advanced systems like Mercedes' active body control and Audi's predictive suspension use hydraulics exactly as Magès envisioned. They've added electronics, cameras, and computer control, but the fundamental architecture, hydraulic cylinders actively controlling suspension movement, remains unchanged from his original design. These modern systems can scan the road surface ahead using forward-facing cameras and adjust suspension settings before the wheels even hit a bump, achieving ride quality that Magès could only dream of. But the DNA is unmistakably his. The most telling validation came in 2017, when Citroën themselves introduced progressive hydraulic cushions after abandoning full hydropneumatic suspension due to cost pressures. After years of trying to match the ride quality of Magès' system with conventional setups, they realized they needed his benefits to remain competitive in the European market. The new system uses hydraulic bump stops that provide the progressive damping characteristics Magès originally achieved with gas spheres. It's simpler and cheaper to manufacture, but it's still fundamentally his core idea adapted for modern production realities. Consider the modern McLaren Supercar. Their proactive chassis control system uses interconnected hydraulic dampers to eliminate body roll entirely without traditional anti-roll bars. Hydraulic fluid transfers between dampers based on cornering loads, exactly like Magès' system transferred fluid between cylinders to maintain level ride height. McLaren's engineers have openly acknowledged studying Citroën's original patents when developing their system. The connection isn't coincidental, it's direct lineage. Paul Magès retired in 1973, having spent nearly 30 years perfecting his suspension system. He held over 100 patents related to hydraulic suspension and vehicle dynamics. He passed away in 1981, just as the automotive world was beginning to embrace the electronic control systems that would finally make his vision of fully adaptive suspension mainstream. He never lived to see his ideas become industry standard, which is one of the great injustices of automotive history. His legacy, however, is everywhere in modern automotive engineering. Every car with air suspension, every vehicle with adaptive dampers, every system that maintains ride height automatically regardless of load, they all trace their engineering DNA back to Magès' workshop at Citroën. He proved that hydraulics could do far more than provide power steering assistance. They could fundamentally transform how a vehicle behaves, responds, and interacts with the road surface beneath it. The numbers tell the story with remarkable clarity. According to production records from the PSA Group, Citroën produced over 9 million vehicles equipped with hydropneumatic suspension between 1955 and 2017. Rolls-Royce used the technology for 15 consecutive years on their flagship models. Mercedes-Benz reportedly spent over $500 million developing their active body control system based on principles Magès established. Today's global luxury car market, worth over $500 billion annually according to J.D. Power Market Analysis, relies heavily on suspension technologies that he pioneered in a small Parisian engineering department. But perhaps Magès' greatest achievement wasn't technical at all. It was philosophical. He demonstrated that engineering conventions exist to be challenged, that complex problems sometimes require complex solutions, and that a small team with a radical idea can out-engineer the world's largest corporations. In an era of corporate groupthink and risk aversion, Magès stood as living proof that individual genius and stubborn persistence still mattered more than budget size or market share. The Citroen DS remains one of the most influential cars ever built. It sits in the permanent collection at the Museum of Modern Art in New York. It was voted the most beautiful car of all time by Classic and Sports Car magazine. But its real beauty was invisible, hidden inside hydraulic lines and nitrogen spheres, inside pressure valves and height correctors buried beneath the bodywork. It was the beauty of engineering perfection, of solving an impossible problem with elegant physics rather than brute force. Today, when you see a Range Rover maintaining perfect composure over rough terrain, or a Mercedes S-Class gliding over potholed city streets, or a McLaren cornering flat at speeds that defy common sense, you're witnessing Paul Magès' vision realized in metal, rubber, and hydraulic fluid. He didn't just outsmart his colleagues at Citroën with a clever hydraulic trick. He outsmarted an entire global industry that told him his ideas were too complex, too expensive, and too radical for the real world. The automotive industry eventually learned what Magès knew all along: that comfort and performance aren't mutually exclusive goals. That complexity in service of perfection is a worthwhile investment. that hydraulics could indeed revolutionize vehicle dynamics in ways that steel springs never could. It just took the rest of the world roughly 60 years to catch up to what one Belgian engineer figured out with a slide rule and a pressure gauge. Modern engineers, armed with computer simulations, finite element analysis, and electronic control systems, still struggle to match what Magès achieved with purely mechanical components. His hydropneumatic suspension remains a masterclass in engineering elegance, complex enough to solve the problem completely, simple enough to manufacture at scale, and reliable enough to last decades with basic maintenance. That's an extraordinarily difficult balance to strike, and most modern engineering teams with vastly superior tools still can't manage it consistently. The irony is genuinely delicious when you step back and look at the big picture. American manufacturers dismissed Magès's invention as an unnecessarily complex science experiment while spending billions of dollars developing inferior alternatives that never matched its performance. They called it impractical while it was winning international rallies and setting speed records across Europe. They claimed customers wouldn't pay the premium while Rolls-Royce was licensing it for their most expensive and exclusive models. The disconnect between corporate perception and engineering reality was staggering, and it cost Detroit decades of competitive advantage in ride and handling refinement. In the end, Paul Magès didn't just design a suspension system. He designed the future of automotive chassis control. Every modern advancement in the field, from electromagnetic dampers to predictive camera-based suspension, builds on foundations he laid in the 1950s. He proved that one engineer with genuine vision and relentless determination could change an entire industry's trajectory. And that's the real secret of his hydraulic system. Not the technical details of how nitrogen gas compresses inside a sphere, or how height correctors maintain ride level, but what the entire project represented. The triumph of innovation over convention. The victory of engineering excellence over corporate conservatism. The enduring power of solving problems that everyone else declared impossible. So here's the question I want to leave you with. What revolutionary technology is being dismissed right now, today, as too complex or too expensive? What modern-day Paul Magès is working in relative obscurity on the next breakthrough that will make today's cutting-edge systems look as primitive as leaf springs? That's the question worth asking, because if automotive history teaches us anything, it's that the next revolution probably won't come from where we expect. It'll come from someone willing to challenge everything we think we know, just like a quiet Belgian engineer did in a Parisian workshop 70 years ago. If you enjoyed this deep dive into one of the most underappreciated engineering stories in automotive history, make sure to subscribe to Motorsport Heritage for more stories of innovations that quietly changed the world. And let me know in the comments, what forgotten automotive technology do you think deserved far more recognition than it received? I read every single comment, and some of the best video ideas come directly from you guys. Until next time, keep questioning the conventional wisdom, because the most interesting stories in motorsport and automotive engineering are almost always the ones hiding in plain sight.